In this video, I'm going to derive the 30, 60, 90 rule for right triangles. And to come up with it, I'm going to just play around with right triangles and see if I can just come up with the 30, 60, 90 rule. So when I use the word derive, I mean I'm kind of starting with just some known facts from maybe a geometry setting, and then just manipulate some stuff to hopefully come up with a relationship between the side lengths of a 30, 60, 90 right triangle. So first, I'm going to start off with a 30, 60, 90 right triangle. So off to this left over here, I'm going to construct a 30, 60, 90 right triangle. I'm just going to say triangle X, Y, Z. And I'll do my best to sketch out a 30-degree angle, come straight down to create my 90-degree angle, and I claim I've created a 30, 60, 90 right triangle. I'll label this vertex X, the high vertex Y, and then the right vertex Z, and we label the corresponding side lengths with lowercase letters. So the hypotenuse in this example is little z, and I want to be height of X, and I want to be base of Y. And I'm just playing around. I think what I'll do is I'm going to reflect this triangle about Y. So I'm going to reflect triangle XYZ about the side length Y to construct a new triangle. And I'm going to say the word similar. Similar triangles should maybe mean something to you. And I'll call this one WXZ, or maybe XWZ. So I just come down. That 30-degree angle, which was going up and to the right, is now being reflected, so it's going down and to the right at 30 degrees. Let's see, 3 marks right there. Maybe something like this. Straight up. It's going to recreate the right angle. It's going to recreate this 30-degree angle. And it's going to recreate this 60-degree angle. I'll call this new vertex W. So Y, the side length that we reflected about, maybe we could also call that little w. The side length X has just been reflected below. So we have another X sitting right here. And then Z has been reflected. This length is still going to be a distance of Z units. And now there's just some things I just want to maybe notice about this new creation I've created. This 30-degree angle is congruent to this 30-degree angle. This 60-degree angle, I'll do a double arc, is equivalent or congruent to this 60-degree angle. This side length is equal to that side length. That side length is equal to that side length. Lots of equality here. Ooh, look at this. What is 30 degrees plus 30 degrees? That means this angle X, this big angle, would measure 60 degrees. So if I ignore Y for a little bit, and I look at the bigger triangle, triangle XYW, that triangle is a 60 degree, 60 degree, 60 degree triangle. We call that an equilateral or equilateral triangle. All 3 angles are the same, and all 3 side lengths are the same. All right, I'm going to write down some of the stuff that we noticed. So my first notation here, I say angle Y is congruent to angle W. This symbol with the equal sign, with the tilde on top, that's congruent. It's like equal measure when you're measuring angles. And maybe I'll differentiate these two x's so I can talk about them. I'm going to say x sub 1 is equal to x sub 2. I think I'll say angle YXZ is congruent to angle WXZ. So YXZ was this original 30 degrees, and then WXZ is this second 30 degrees. They are equal. And now I'm ready for that gasp moment where we say 30 plus 30 is 60. So the bigger triangle is an equilateral triangle. All right, so I had a 30, 60, 90 triangle and just kind of reflected it down. And then I have this bigger 60, 60, 60 triangle. Let's see. Well, that means all three side lengths are the same. So we have Z, maybe I'll differentiate these. This is Z sub 1, Z sub 2. And then this side length will also be equal to that Z measure. I'll call it Z sub 3. So X and X, when you add them together, become this same side length Z. I think I'll write that down too. Oh, another way to say that is I could add these like terms because X is equal to X in this game. So we have two X's are equal to that Z distance. I think I'll solve for X. We did that in a previous video. X is going to be equal to Z over 2. Now what we have here is a cool relationship between X and Z. Now I don't want to harp too much on the variables, so let's turn this relationship into English, and instead of using X, let's come up with a better way to describe X. So I'm looking again at my original triangle, the 30, 60, 90 triangle, where I have X and Z. Z is the hypotenuse of the triangle, and X is one of the side lengths. Y is another side length. Well, X is the side length opposite the 30-degree angle, whereas Y is the side length opposite the 60-degree angle. So I think a good way to describe X is that it's the shorter side. The side length opposite 30 degrees will always be shorter than the side length that's opposite the 60-degree angle. So I'm going to take this relationship and turn it into maybe some English, or just to spit out a rule for this. And I just claim that the shorter side of any 30, 60, 90 triangle is going to be equal to the hypotenuse divided by 2, always and forever. So just a quick little example. If you have this triangle, 30, 60, 90 triangle, and the hypotenuse is 10, and you want to find that x value over there. How could I find the value of x? Well, x represents the shorter side length, the side length that's opposite 30 degrees, and that is always going to be equal to the hypotenuse divided by 2. So x is simply going to be 10 cut in half, which is a nice pretty 5. Cool. Okay, I think we can go further. If I know how x is related to z, I think I can go back to my original xyz triangle and play around with the Pythagorean theorem. Let's do that. I'll switch over to new paper. So Pythag says x squared plus y squared equals z squared, where in my example, x and y are side lengths and z is the hypotenuse. But we know what x is. We just said x, the side length opposite the smaller angle, is going to be z over 2. I'm going to make that substitution. X can be rewritten as z over 2. Okay, now I have an equation with only y's and x's. I think I'll solve this equation for y. To do so, I guess I can square this out real quick. If you have a fraction squared, you can square both numerator and denominator independently. I think what I'll do, because I have the equation sign, I'll just multiply everything by 4 to get rid of any denominators. That's going to make it easier to subtract one z squared over to the other side of the equation and combine my z squareds. If I want to solve for y, I'll first divide both sides of the equation by the coefficient 4. And then if I want to find the square root, I can take the square root of both sides. If you take the square root of a product like we have up top and a quotient, you can do them all independently. So this is equal to a z in the numerator, a square root of 3 in the numerator, and we know the square root of 4 is 2. All right, this is a pretty cool relationship. Y is equal to z times the square root of 3 over 2. Or, what was z over 2 previously? Z over 2 is that shorter side length. So the longer side length is just the shorter side length being multiplied by the square root of 3. Nice. Okay, so I now have a relationship for the short side length, the long side length, and the hypotenuse of a 30, 60, 90 triangle. I'm going to write it down formally in English, something like this. I claim if you have a 30, 60, 90 triangle, the shorter side length equals the hypotenuse divided by 2, or just cut in half. Then the other side length, or the larger side length, is that value being multiplied by the square root of 3. All right, let's do some quick examples of just using these rules and maybe getting comfortable with them. All right. Let's say we have this triangle. We know we have a right angle. We know this angle equals 30 degrees. we know this side length is 12 and this side length is little b. That side length is little a, and we are asked to find both a and b. Okay, well, I know this is a 30, 60, 90 triangle because if this angle measures 30 and that's 90, well, there's only 60 degrees left out there. So we're in the 30, 60, 90 situation. And I know the shorter side length, the side length opposite the smaller angle, A, will be equal to the hypotenuse divided by 2, which is 12 divided by 2, which is 6. So A measures 6. The rule continues. It then says that the larger side length, B, is the shorter times root 3. So little b must be 6 times the square root of 3. So I'm able to, just using this rule, calculate the side lengths of the triangle. A was 6, and b is 6 times the square root of 3. All right, let's do it again. All right, 2 examples. Pause the video, see if you can find x and z and a. Now the first example is a 30, 60, 90 rule. So the shorter side length is half the hypotenuse. So let me write that down. The shorter side length is half of the hypotenuse. So that's just that rule. The shorter side length, which in this game is 3, is equal to the hypotenuse z over 2. So I can find z by multiplying both sides of the equation by 2. 6 must be z, the hypotenuse. Now the other side length, x, this is the larger one, it's going to be equal to the shorter one times the square root of 3. The larger side length is equal to the shorter one times the square root of 3. So don't let variables confuse you. You're actually looking for the shorter side, the larger side, and the hypotenuse. In the next example, this must be the isosceles. These little bars mean those two legs are congruent. So both of these are A. I'm trying to find A, and I only know the hypotenuse. Well, the 45 rule was mentioned in a previous video, but it said the side length will always be equal to the hypotenuse divided by the square root of 2. So we have the square root of 2 divided by the square root of 2, which is 1. So these two side lengths are equal to 1. All right. I hope that was fun. I'll see you in the next video.